In today's lesson, we're going to learn reactions related to aldehydes and ketones. So, first, let's review the structure for aldehyde and ketones. Aldehyde, it has a carbonyl group at the end of the carbon chain. And for ketones, the carbonyl group should be placed in the middle of the carbon chain. Okay, so from previous lesson, we have learned if we have primary or secondary alcohol, we can oxidize it using potassium dichromate with acid. Then we will be able to make those alcohol into aldehyde and ketone. So today we're going to learn two types of reaction. First, we can do oxidation for aldehyde, and then we can turn it into carboxylic acid. And then for ketone, remember, we cannot further oxidize it, so it would have no reaction with potassium dichromate with acid. Okay, and also we can go backwards. If we have aldehyde or ketone, we can reduce it to form primary or secondary alcohol. Let's revise the first reaction, oxidation of aldehyde to form carboxylic acid. Remember here, the oxidizing agent we used is potassium dichromate, and together with acid, it's in acidic condition. And for this reaction, we need to heat it on a reflux to get the product, which is a carboxylic acid. Okay, so let's quickly go through the examples here. So first example, we have an aldehyde. We can highlight the carbonyl group, which is here. So after oxidation, the carbonyl group will be turned into COOH, and then we can draw the final product. Okay, so the rest of the carbon chain stays the same, and then the carbonyl group now becomes COOH. And make sure you fill in the rest part with hydrogen. Okay, so that's the first example. Second example, again, we highlight the carbonyl group first. This one is an aldehyde, so if we put it with potassium dichromate in acidic condition and then heat it, then we will be able to oxidize it and turn into an carboxylic acid. Okay, so here we turn the C double bond O to COOH group, and then we write the rest of the carbon chain. Okay, and then next example, again the C methanol. We have the carbonyl group at the end, so if we put it with potassium dichromate in acidic condition and then we heat it, it will undergo oxidation and then it will form a carboxylic acid. Okay, so that's the methanoic acid. And finally, the last example, again let's highlight the carbonyl group. For this one, the carbonyl group is in the middle of the carbon chain, so here this one is a ketone. Okay, so remember, if we put ketone with the oxidizing agent potassium dichromate in acidic condition, there will be no reaction. Okay, so you just put a cross for that. Now let's move on to the second type of reaction related to aldehyde and ketones, the reduction reaction. Also, this type of reaction we name it as nucleophilic addition reaction. Okay, so here I want to remind you the opposite of reduction should be oxidation. Okay, so not the addition. Okay, addition has no relationship to the reduction. Okay, so in this part, we're going to use two reagents. First one is called the lithium aluminium hydride. And the second one we are going to talk about is called sodium borohydride. Let's focus on the first reagent, which is lithium aluminium hydride. Okay, I have attached the structure for that reagent here. So here you have the lithium cation, and then you have this called a complex ion. So later we will have a unit that talks about the complex ion. But for now, you just remember the complex ion, aluminium hydride, overall it carries 1 minus charge. That's because aluminium here is from group 3, so it will carry 3 plus. And then each hydride will carry 1 minus. So overall, it will have 1 minus charge for that complex ion. And for lithium aluminium hydride, you need to remember it is a very strong reducing agent. Okay, hence it will react vigorously with water. So whenever we are using lithium aluminium hydride, we must carry the reactions in anhydrous condition. That means no water is presented. So here I would like to show the video what will happen if we react lithium aluminium hydride with water. You can see from the video, when we add water from the dropping bottle, it actually causes an explosive reaction. So remember, when we are using lithium aluminium hydride as a reducing agent, we must carry the experiment in an anhydrous condition. Okay, so here, in order to carry it in an anhydrous condition, what are we going to choose as a solvent for the reaction? So here I want to introduce a solvent called anhydrous ethoxyethane. Okay, or sometimes you may hear that people call it diethyl ether. Okay, so the structure is like this. It's similar to a person that's swimming. Okay, that's a head, that's 2 arms. Okay, so for this one, that's a common organic solvent, and we can make it dry, or sometimes we also call it dry ether. Okay, so that's the first type of reagent. And then let's move on to the second type. Second type is called sodium borohydride. Again, we have sodium cation and then a complex ion formed here. So for this one, for sodium borohydride, it's a less powerful reducing agent than lithium aluminium hydride. So we can use it in water. So we can actually react with sodium borohydride with aqueous solution. So for that reason, we often choose it because we can handle it safely in the lab. Okay, but there is disadvantage for that one because it's less powerful compared to lithium aluminium hydride, so it's not strong enough to reduce carboxylic acid, which we're gonna talk about in the next part of this unit. So to summarize, there are 2 options we can choose to do reduction for aldehyde and ketone. The first one is using lithium aluminium hydride in dry organic solvent, dry ether or dry diethyl ether. That's okay. For this part, it's actually 2 steps reaction. Let's take a look at the mechanism. So this mechanism is not required in the syllabus. So here I would just like to state that this process is a 2 steps process here. So the first part, the lithium aluminium hydride or sodium borohydride would act as a nucleophile. So it would attack the slightly positively charged carbon, and then it would push the electrons to the oxygen here. And then in the second step, it will react with the acid. Okay, so it would actually remove the proton from water, which is this one, and then it will reform water in the solvent. Okay, so that's step 1. The nucleophile attach the molecule, and then second step is the taking of the proton to form the alcohol. Okay, so let's go back to this part, the summary part. So that's the first choice. Remember, it's 2 steps. You need to label it, step 1, step 2, and label the reagent needed. And the second choice, you can choose sodium borohydride. Okay, so for this one, we can carry this experiment in aqueous solution, so you can write the solvent as water. That's okay. Okay, so let's try to work out some examples together. So the first example, we have an aldehyde. So again, let's highlight the carbonyl part. So after reduction reaction, the C double bond O carbonyl will change back to OH group. So let's write that part first. Okay, and the rest of the carbon chain will stay the same. So let's complete the rest of the carbon chain. And make sure you fill in the hydrogen. Okay, and for the second example, we have a ketone. Again, we highlight the carbonyl group. And for this example, the reagent we use here is lithium aluminium hydride, and the solvent is dry diethyl ether. And after 2 steps, and we should get an alcohol. So the alcohol again would turn the double bond O to OH, and then the rest of the carbon chain stay the same. And remember to fill in the rest of the hydrogen. Okay, and the third example, again, let's highlight the carbonyl group here. In the reagent, you can either choose lithium aluminium hydride in dry diethyl ether followed by an acid, or you just simply choose sodium borohydride in aqueous solution. Okay, so make sure you label the reagent clearly. So here I will use sodium borohydride in water. Okay, so after the reduction reaction, I will be able to get the alcohol. So the alcohol again would have the rest of the carbon chain stay unchanged, and then I would have the alcohol formed. Let's move on to the checkpoint questions. Please pause the video here, attempt all the questions, and then listen for explanation. Question 1. Consider the following reaction of butanone. Which of the following combination is correct? So for butanone, it would not be able to carry oxidation reaction to form carboxylic acid. And then you can see here we got an oxygen in the formula that indicates after the reaction it will be converted to an alcohol. Okay, so this reaction is a reduction reaction. So we need to choose reducing agent. So we should choose our answer from C or D. Okay, and then let's take a look what gonna be the product. So here we need to first draw the structure of butanone. So for butanone, okay, first we need to draw 4 carbon, and for butanone, the carbonyl group must be placed in the middle of the carbon chain. And it doesn't really matter which side you put, because you have to make sure that it got the lowest number, so it's always at the second carbon. Okay, so after the reduction reaction, the carbonyl group would be changed to COH group, hydroxyl group. Okay, so you can see the hydroxyl group would be formed at the second carbon. Okay, 1, 2. It will be placed at the second carbon. So we should name it as butan 2O. So the correct answer for question 1 should be D. Okay, and then let's move on to question 2. Question 2. Which of the following alcohols is optically active and could also be oxidized to an aldehyde? So let's check the answer one by one. First, A. We have 2-methylbutan-1O. Okay, so let's draw the structures together. So for 2-methylpropan-1-O, it should have this structure. Okay, and then we have the hydroxyl group, and then we have the methyl group. So I won't add the rest of the hydrogen just to clearly show the structure here. Right, so for this molecule, first let's check whether it's optically active or not. Okay, so if we take a look, we can actually see this carbon. Okay, so this one, if I draw the hydrogen here, it attached to 4 different groups of atoms. So this carbon, we can say, is a chiral carbon. So this molecule is optically active, and then we need to examine whether it can be oxidized to an aldehyde. So remember, only primary alcohol can be oxidized to an to aldehyde. So this one, that's a primary alcohol. So it fulfills both requirements. So A should be the correct answer. Let's go through the rest of the choice and double check our answer. So for part B, we have 3-methylpentan-2-O. Okay, so let's draw the carbon chain first. And then we have pentan 2O, so OH group at the second carbon, and then the methyl group at the third carbon. Okay, so again for this one, you can find the chiral carbon. It actually got 2 chiral carbons here. Okay, so this one and also this one. So it's optically active, yes, but then we need to also check whether it can be oxidized to an aldehyde. So this one is a secondary alcohol. So secondary alcohol will be oxidized to an ketone, not an aldehyde. So B is not the correct answer. Okay, and C, we have 3-methylpentan-3-O. Okay, so again, draw the structure first. Let's draw the carbon chain first, and then we have the hydroxyl group attached to the third carbon, and we have the methyl group attached to the third carbon. So for this one, can you find any chiral carbons here? You can see if we pick this carbon, although it has a hydroxyl group and a methyl group attached to it, but on both sides it has an ethyl group attached to it, 2 identical groups of atoms. So there's no chiral carbon. This is not optically active. So this one doesn't fulfill the first requirement. Also, let's check whether it can be oxidized. So this one is a tertiary alcohol. So for tertiary alcohol, we cannot oxidize it. Okay, so it doesn't fulfill any requirement here. Okay, let's check the last choice. We have propan-1-O. So draw the structure. It will look like this. Again, for this one, we cannot find any chiral carbons here. Even with this carbon, it got 2 identical hydrogens attached to it. So this is not a chiral carbon. So this molecule will not be optically active. And it's a primary alcohol, so yes, it can be oxidized to an aldehyde, but since it doesn't fulfill the first requirement, so we would not choose it. So we have confirmed our answer should be A. Okay, let's move on to the third question. Which of the following reagent can be used to distinguish between propanol and propanone? Okay, so first one, if we use potassium dichromate in acidic condition, propanol would be oxidized to carboxylic acid, but there would be no reaction with propanol. Okay, so if we put propanol with a reagent, it would turn into propanoic acid, but there's no reaction for propanol. Okay, and for the second one, we have lithium aluminium hydride with dry ethoxyethane. Okay, so for this one, it will undergo reduction. So remember, we have just talked about this kind of reaction in this lesson. So both aldehyde and ketone would undergo reduction to give alcohol. Okay, so both of them will turn into alcohol. But one of them gonna be turned into, the propanol will turn into primary alcohol, propanone will be turned into secondary alcohol. And for C, we have sodium borohydride in water. Again, it will undergo reduction, and both of them will form alcohol for this. And finally, the last one, PCl5. Although we didn't learn this in our syllabus, but PCl5 will react with both of the reaction. And for propanol, so propanol we have CC. Okay, again I will not draw the hydrogens here. So for that one, it would turn into Cl2. Okay, and again you need to fill in the rest with hydrogen. Okay, and for propanone, it will also have reaction, and it will be turned into this. Okay, and remember to fill in the rest of the hydrogens. So the correct answer should be A. Okay, only propanol will react with the reagent. Propanone will show no reaction, so we can distinguish between these two reactants. Question 4. The organic product of the above reaction is, so for this one, we have an aldehyde, and then it will undergo reduction with sodium borohydride. Okay, so let's draw the structure of the product first. So after reduction reaction, the C110 would turn into OH group. So this alcohol we get should be like this. And then remember the alcohol group, the functional group should have this lowest number, so we should label carbon 1, carbon 2. Okay, so it should be called 2-phenyl ethanol. So the correct answer should be D. Last question. Which of the following statements about 3-methyl-butanone are correct? Okay, again, for easier understanding, I will draw the structure first. So for this one, we first draw the butanone part. Okay, and then we should draw the 3-methyl part. Okay, again here, to show the structure clearly, I didn't label all the hydrogens here. So let's check. Statement 1, it reacts with sodium borohydride to give a secondary alcohol. Okay, that's correct. Okay, so because it's a ketone, so it will undergo reduction to give a secondary alcohol. And then second, it has an isomer of pentane 4-in-1-O. Okay, so if we draw the structure for pentane 4-in-1-O, it should look like this. And then OH group here. Okay, and make sure you write all the hydrogen out. So both of them have a molecular structure as C5H10O. So yes, it has an isomer of pentane 4-in-1-O. And lastly, the last statement, it has no reaction with lithium aluminium hydride. If we put this 3-methyl-butanone with lithium aluminium hydride in dry ether and then react with an acid, we can reduce it to an alcohol. So that's a wrong statement. Okay, so the correct answer should be A.